My name is Doug Laporte. I'm a design manager for signal conditioning products at Linear Technology. I'm going to talk about general timing functions and a new family of products that we've designed to address the needs in this area. Timing functions such as low-frequency oscillators, VCOs, PWMs, one-shots, and delay blocks are presently being served by either general-purpose timers, which suffer from poor accuracy, or by custom-coded microprocessors, which add unnecessary development time, complexity, and documentation. Today we're introducing the Timer Blocks family of compact, easy-to-use, and accurate timing functions to meet these needs. So instead of designing one-size-fits-all type timing parts, we decided to focus on making a family of individual targeted parts. The initial offerings in this family are 5 parts: a silicon oscillator with VCO capability, a resettable low-frequency oscillator, a voltage-controlled pulse width modulator, a monostable pulse generator, or a one-shot, and a programmable delay. First, let's take a look at some basic features common to all members of the Timer Blocks family. The basic application schematic here is common to all members of the family. The main difference is the function of this pin up here, which I'll call the part-specific function pin. This purpose varies on each part and has a unique function. Looking at this schematic, one thing that will jump out at you right away, is obvious, is that there are no timing capacitors. This is a key feature on this part. Your circuit doesn't have to suffer from the wildly varying temperature coefficients associated with many capacitors. Also, you don't have to source hard-to-find specialty capacitors. We take care of the tough stuff inside the part. All you need to do is provide a resistor. What you get in return for this resistor is a timing function with 2.2% maximum error over temperature, and that temperature is the full minus 40 to plus 125 degrees Celsius temperature range. Fast and reliable startup is common to all parts, and it's only a few milliseconds. Wide operating supply range from 2.25 volts to 5.5 volts is common to all parts. Each part also has a very strong output capable of syncing and sourcing at least 20 milliamps. All of these good things come in one nice small little package with your choice of a 6-lead thin SOT or a 2x3 DFN. Note these 2 resistors over here. These set up a voltage on the divider pin, or div pin for short, that's read by an on-chip 4-bit A to D converter to program an internal frequency divider that sets up also a control bit. The 3 least significant bits of the A to D converter program the frequency to one of 8 states. This allows the part to cover a very wide frequency range. The A to D's most significant bit sets up a control bit that in most cases determines the polarity of the output, be it inverted or not inverted. This div pin's A to D converter is designed to use standard 1% resistors between the supplies. It has substantial voltage hysteresis and significant digital post-processing to maximize the robustness of this circuit for interfering signals. Now let's look at each part individually. The first part in the family is the LTC6990 oscillator with VCO capability. This part has a frequency range of 488 Hz to 1 MHz, and when used as a VCO, it has a full tuning range of up to 16 to 1. It has a maximum frequency error of only 2.2% over the entire operating temperature range. Now with this set pin here, derived from an on-chip precision bandgap reference, the addition of a single resistor, RVCO here, allows you to control the frequency by a simple voltage, in other words, create a VCO. You can intuitively see that if V control is pulled down to ground, RVCO and RSet are now in parallel, and the resulting output frequency is as you would expect from a parallel combination. As V control is pulled up some, less and less current comes out of the RVCO and out of the set pin, thus decreasing the frequency. The oscilloscope photo over to the right illustrates this clearly. You can see that as the control voltage increases, the output frequency decreases. Additionally, by simply changing the ratio of these 2 resistors, the designer can make the VCO optimized to provide just the amount of tunability needed for the application and no more. Let's move on to the next part. The next part in the family is the LTC6991 resettable low-frequency oscillator. The key feature of this part is its very low operating frequency with a period as long as 9.5 hours. This part also maintains the 2.2 frequency percent error over all conditions. The example application shown here is a power-saving wake-up timer. The LTC6991, its output goes high once every T out period, which again can be as long as 9.5 hours. This activates the switching regulator and turns on the system. When the system is done doing its job, it tells the LTC6991 to go low, which in turn turns the switching regulator off and it comes back up the next cycle. If this reset signal is held low, then the output signal is simply a very low frequency square wave that has a high side of 488 Hertz and go down as low as 29 microhertz. Yes, microhertz. The next part in the family is the LTC6992 voltage-controlled pulse width modulator. Here, the part-specific pin is the mod pin. This pin is a high-impedance analog input that modulates the duty cycle of the output voltage. A control voltage on this pin, call it VMod, ranging from 0 to 1 volts, sets the output duty cycle directly. The part operates from 3.8 Hertz to 1 megahertz and a pulse width duty cycle accuracy of 4.5% maximum and a frequency error of 2.4% maximum. The LTC6992 is available in 4 different versions, each with its own duty cycle range. The LTC6992-1 covers the entire 0 to 100% duty cycle range and can deliver controlled pulse widths as narrow as just a few nanoseconds when approaching each limit. The LTC6992-2 has internal clamping circuits to limit the duty cycle from 5% and 95% as required by many safety-conscious applications where the output signal must be monitored and must always be active and must never be DC. The LTC6992-3 has a high side clamp only and covers the 0 to 95% duty cycle range. And lastly, the LTC6992-4 has only the low side clamp and covers the 5% to 100% duty cycle range. The other thing to note with this part is that the most significant bit of the div pins A to D converter sets the output signal's polarity as inverted or non-inverted. Inverting the output signal here has the effect of changing the polarity of the transfer function of the duty cycle from increasing with VMod voltage to decreasing with VMod voltage. The scope photo here at the bottom illustrates the LTC6992-1 in action. As the VMod voltage goes below ground and above 1 volt, the duty cycle goes to exactly 0 and exactly 100%. In the middle, the duty cycle is proportional to the VMod voltage. The next part in the family is the LTC6993 monostable pulse generator, or one-shot. This part also has 4 different versions covering which edge is triggered, be it rising or falling, and whether it's retriggerable or non-retriggerable. The one-shot time range is 1 microsecond to 34 seconds. By combining the triggering selectability with the ability to select the output polarity via the div pin A to D, all possible I/O combinations are available. Additionally, the retriggerable and non-retriggerable versions cover all conceivable one-shot needs, and the maximum pulse width error is only 3%, again over the full temperature range. To illustrate the retriggerable feature, let's take a look at the 2 scope photos down here. The first photo shows an LTC6993-1, a non-retriggerable part, set up to produce a 16 millisecond wide pulse, and is being hit with 2 rising edges in quick succession. Since the second rising edge here is before the one-shot times out, it's ignored. In other words, the part is not retriggered and it just goes low at the end of 16 milliseconds. The second scope photo shows the LTC693-2, a retriggerable part in the same configuration being hit by the same input signal. In this case, the part acknowledges this second rising edge, is retriggered, and the pulse extends an additional 16 milliseconds. Our last part in the family is the LTC6994 programmable delay, which comes in 2 versions. The LTC6994-1 delays only one edge. The polarity of that edge, whether it's rising or falling, is set via the div pins A to D. The LTC694-2 delays both edges, but the polarity of the output, inverted or not inverted, is selectable again via the div pins A to D. Each part has a programmable range of 1 microsecond to 34 seconds and a maximum error of 3%. These 2 scope photos illustrate the difference between the 2 parts. The first photo shows the LTC694-1 set up to produce a 16 millisecond delay being excited by 2 pulses. You can clearly see that only the first edge is delayed and that the second edge is coincident with the input signal. The second scope photo shows the LTC6994-2 in the same configuration and demonstrates two features. First, both edges of the first pulse are delayed 16 milliseconds as expected. Next, note that the second pulse is ignored as it is only 15 milliseconds wide and is narrower than the program's delay. This is very useful for switch debouncing as well as pulse width qualifier applications. As you can see, the TimerBlocks family of products provides a new way to tackle your general timing function needs that is compact, easy to use, and precise, without the inaccuracies and uncertainties associated with general purpose timers or the hassles of developing, documenting, and maintaining microprocessor code. For additional information on these products, please visit our website at www.linear.com, where you'll find all the data sheets for all these parts, as well as their LT Spice macro models and TimerBlocks design tool software to get you up and running instantly. Thanks for watching.